Hello, everyone. Thank you for attending our presentation today on powder life. Today, we are going to talk about managing risk, enhancing safety, and optimizing economics in additive manufacturing. My name is Gaurav Lalwani. I'm the Global Applications Engineering Lead for Carpenter. I work with the medical team, and today we are talking about the recent developments that Carpenter technology has done over the last few months with improving powder management. So quickly to just go over the agenda, I'll go over an introduction about Carpenter technology, what we have to offer. Then we'll get into the importance of high quality additive manufacturing powders for the medical device industry. We'll talk about powder life, which is the topic of our conversation. And at the end, we'll summarize Carpenter's end-to-end manufacturing capability. So Carpenter Additive is a fully integrated end-to-end supplier of additive manufacturing products that includes powders for additive manufacturing, solutions for powder handling, and life cycle management, and essentially finished components. Carpenter has invested about $200 million to date in additive manufacturing and scattered across different areas. We have 4 R&D centers that focus exclusively on additive manufacturing, several different platforms, equipment including different manufacturers. We have EOS systems, SLMs, 3D systems, trunk machines, X1, Optomac, RCAM, and concept lasers. So essentially covering the entire gamut of equipment available from all of these manufacturers. And we have a robust team of about 40 R&D and project management staff from industry and academia, where we definitely and regularly collaborate with them on new products. On raw material, we deal with powder supply on titanium, nickel, steels, and aluminum powders. We have a global footprint of powder atomization capability scattered across multiple sites over 2 continents. We are the world's largest gas atomized powder producers in the world. We also produce a lot of titanium wire feedstock and essentially can make more than 500 alloys that can be further processed into powders for additive manufacturing. And that includes all of the standard alloys as well as any customized productions that customers might need. As far as parts are concerned and production of parts using additive manufacturing, Carpenter has experience with thousands of build cycles. Our facility in California is NADCAT AS9100D certified. We have long-range programs and as well as pilot scale programs, depending on the customer needs. We also offer post-processing treatments like hipping and heat treating all under one roof. And we use powder lifecycle management to further optimize the process and raw material that we use for additive manufacturing. As I said, materials innovation is in our DNA. We are driving the technologies of the future with additive. We have a world-class R&D with expertise across different platforms, equipments, and a robust infrastructure for true end-to-end additive manufacturing. We have an expansive brand of alloy portfolio of really proven high-performance alloys. We have more than 200 metallurgists on staff and access to other industry and academic experts. And we are talking here about true end-to-end additive solutions, whereby we take your designs, are able to produce powders, and take that all the way to full-scale production. So moving forward, what Carpenter envisions and has to offer in this space is essentially to be a partner in a total solution for the entire life cycle of additive manufacturing. And that includes our powder range offerings, which is an extensive selection of off-the-shelf custom alloy powders for additive manufacturing that are optimized for AM. Powder Life, which is one-of-a-kind industry-leading raw material lifecycle management solution package, which helps reduce risk, improve safety, and optimize the build economics with full material traceability. And we also have manufacturing services where we offer full metal additive manufacturing production and quality management to our customers, where we take the designs from powder to part on one of our 4 additive manufacturing campuses, all under one roof. So why are we talking about additive manufacturing, and especially how is it relevant for medical devices? As we all know, additive manufacturing has been widely adopted in the medical device design community. In fact, medical was one of the early adopters. The first FDA-approved AM implant was launched in 2010. And since then, this has been an extremely fast-growing space in the medical device industry. Until date, more than 150 FDA-approved metallic AM devices exist in the marketplace. And out of those 150, more than 90 were approved in the last 2 years. So there has been a great surgence of additively manufactured medical devices lately. Orthopedics has been the largest driver of AM, and several applications such as acetabular cups and spinal cages are driving that growth in orthopedics. And when you think about it, why is additive manufacturing gaining such a large share and acceptance in this space? Is because it directly and it positively impacts clinical outcomes. With additive manufacturing, the OEMs are able to design porous architectures that facilitate bone-in growth. These porous architectures also help to integrate the implant in a much better and robust way compared to traditionally subtractively manufactured implants. And also, press-fit technology that is enabled via additive manufacturing eliminates the use of cement, bone cement, which can really crack over time and lead to revision surgeries. If you look at the material space, titanium alloy has been the widely adopted material of choice. Specifically, 6-4 Eli grade 23 commands more than 80% of the market share. And recently, there has been a lot of development in other non-titanium alloys such as stainless 316, 174, cobalt chrome, Biro 108, and nitinol. And one common theme that is really critical is to have access to high quality AM powders. Because as you envision the development of next generation medical products with additive manufacturing, in some cases, you need to have access to high quality and better raw material to enable those complicated designs. So towards that, what Carpenter Additive has is a powder range suite of offering where what we do is essentially develop high quality powder that essentially has been engineered to weed out all the contamination. If you look at the image on the right, is essentially a CT scan of a part that is in the process of being manufactured. And the white speck that you see on the image is essentially high density inclusion. Now, what happens is if you have any of these kind of high density inclusions anywhere in your part, in any of the layers, it leads to premature failure. So powder quality is very, very important to enable high quality parts. For that, Carpenter has dedicated manufacturing facilities. So we have in our manufacturing facilities, we have separate processing areas for each alloy category, and none of the alloy categories or alloy families actually overlap. And we operate on clean room principles. And there's strict contamination control. The facilities are climate control, humidity control, for moisture control, with air showers, air logs, and positive air pressures. And it reflects our commitment to quality, where we certify the powder on a robust repeated sampling approach, which leads to high statistical confidence. And we work, and our laboratories are accredited to 17025, which is a very stringent quality control certification, with a range of analytical techniques to identify contaminations that we've developed in-house. So as I said, high-tech, low-contamination manufacturing, and when you talk about titanium and other specialty alloys, we do that across two different sites, one in Athens, Alabama, and the other one in Liverpool, UK. In Alabama, we focus on essentially about 3,000 pounds. We have a 3,000 pound WIM atomizer. We are able to perform argon or nitrogen-based atomization as the gas source. This atomizer has automated pouring capabilities. It has twin towers, so you can clean out one as you are segregating the powder that you produce in the other tower. In our Liverpool facility, we have an IGA atomizer, which is an electron gas atomization process, and that's used for reactive metal powders such as titanium. It's essentially a 1,000 pound. We also have a 1,000 pound Viga atomizer that we use for nickel, cobalt, and other steel alloys. And in this facility, we also have the ability to develop custom powders. We have an in-house plasma spherizer that we use for refractory powders such as tantalum, tungsten, neodymium, and molybdenum. And this facility is ISO 1345 certified with full material traceability capabilities and digital integration. So getting into powder life, why is it important for us to have a solution that enables powder-to-part manufacturing in a closed-loop AM ecosystem? So powder life essentially is a combination of hardware and software solution, and the entire process that goes along with it to drive innovation. And why is it important for us to have complete traceability? Why is it important for us to understand how the powders behave throughout the additive manufacturing life cycle? A major issue in the field right now is to maximize the use of additive materials. And it's an industry-wide problem. And the issues are essentially change in the chemistry of powder with use. So as you use your powder in your AM equipment, it leads to nitrogen pickup and oxygen pickup, which changes the chemistry of the powder. And as you keep reusing the powder, the chart on the left shows oxygen pickup. And after a certain number of reuse cycles, your oxygen levels in the powder actually are above the specification limit, which then, if you still continue to use those powders, is reflected in the parts you build. And that results in variation in mechanical properties of the parts. So how do you actively monitor when your powder goes out of spec to optimize the process and optimize reusability is a critical variable. So for instance, this is just a thought exercise that we put here on this slide. So in this exercise, if you envision that you're producing about 1,000 parts for 15 years, 1,000 parts per year for about 15 years, and you're producing about 10 parts per build, and you're doing 100 builds per year for your 1,000 parts, we're assuming half a kg as the final part. an alloy costs about $80 per kg. So just a thought exercise. So what happens is if you essentially are not recycling and reusing the powder, it leads to an additional material cost of about $18 million. You're essentially wasting 154 kgs of powder per build because you're not recycling, which means you're wasting about 15 tons of powder per year and about $1.2 million of powder per year, if you translate that into cost. For titanium, the cost is going to be higher, so the numbers are going to be significantly higher. Now, if you factor in an arbitrary situation where you're able to reuse the powder 15 times, what you do then is your numbers actually go down significantly, where you are essentially saving 154 kgs of powder per subsequent recycle after the first build. So essentially, instead of wasting 15 tons of powder every year, with the number of recycles that you have in there, you're only wasting about a ton of powder, which essentially translates to about $1 million of powder wastage over a 15-year product life cycle. So figuring out when your powder goes out of spec and optimizing the number of reuses that you can achieve out of a given powder sample is extremely important. Now, what factors affect powder degradation? So when you have your powder in the equipment, essentially a 3D printer, and you hit it with a laser, so we are talking about a laser powder bed fusion printing process here, it leads to a lot of powder splatter. 3D printing on the microscopic scale is actually a very, very vigorous process. And the powder that's splattered across around the area, it essentially picks up oxygen and nitrogen from the build chamber. And that leads to formation of irregularly shaped oxygen nitrogen rich particles that essentially fall back on the same powder bed. And what happens is, as you further now try to optimize and improve the efficiency of your 3D printing process with, increasing the scan area or increasing the laser power, that only increases the spatter, which further leads to an increased uptake of oxygen and nitrogen. So it is important to actively monitor powder quality in the entire life cycle process. So powder suite of solutions is essentially a closed loop powder handling approach that is made possible through the integration of several different components in the AM life cycle. So if you look at the diagram on the screen, we need to have visibility to the feedstock that's being used for atomization. We monitor the chemistry of the powder during the atomization process and post-atomization once it's sieved to different size fractions. Then we actively monitor powder chemistry and powder properties as it's being loaded onto the hoppers and being shipped out to a printing site. Now, within the printers, we have solutions that can actively, again, monitor key powder variables as the powder is being used and as the build is in progress. With all of that, what happens is now you have a robust data set where you have visibility to all powder parameters that are changing after each and every use. And once the powder goes out of specification, you now are able to take the powder out and put it across a recycle where the powders can come back to a facility like Carpenter and get repurposed, which now again are suitable for use for the production process. So essentially, Powder Life suite of solutions is a closed loop powder monitoring process with, of course, different hardware options and a software solution that provides access to all of the key critical process variables throughout the life cycle of an additive manufacturing product. Now, when I'm talking about powder management solutions, what we have essentially are hardware solutions that are designed to improve operational efficiencies and also minimize the risk of particulate exposure to AM operators. So, for instance, we have hoppers that are able to transport more amount of powder than what a typical 5-pound Kurdic jug would do. So you're minimizing a lot of waste, as well as you're transporting powder in an equipment that has sensors built in to monitor oxygen levels, moisture levels of the powder as it's being transported in real time. You can then take this same hopper and essentially put it onto your printer, and that can act as a powder reservoir, which feeds powder as you build in your system, and essentially that minimizes the risk of exposure where you don't have the operator decanting powder out in a manual operation and feeding it into the system. And once the powder is essentially used or consumed or out of specification, you can use the same hopper or a different hopper to further ship the powders back to a facility like Carpenter, where we can recycle the powder and get it fit for an additive manufacturing process again. So Carpenter's powder life cycle solutions are actually necessary to industrialize AM. And again, as I said, these solutions eliminate powder exposure, and they also create a digital thread where you're able to monitor progress from powder to parts, and then you're able to utilize data analytics to further optimize the process and maximize the economics with respect to powder recyclability and powder reusability. So what we see is our customers who implement powder life-based solution, they actually have to carry low inventory of your metal AM powder. There we've seen inventories reduced by over 50%. We've seen cost reductions of about 25%. We've seen quality improve up to 30% by essentially avoiding generation of scrap because of the traceability that's designed in the software. And we also see about 50% reduction in changeover time between the builds through smart agnostic hardware solutions like the hoppers and the powder eye sensors. So with this, I want to take it a step further where we take the designs from powder to part in our vertically integrated metal AM production facility. So many users that essentially are getting into additive manufacturing right now think that the cost is essentially just driven by reuse alone. That if you're able to maximize or use or reuse the powder for more number of cycles, it's going to reduce cost. Now that is true to an extent, but there's a lot more that goes into establishing a sustainable additive manufacturing program. You need to have designs and processes that are optimized for AM. You need to have access to materials. There's a whole parameter and spec development that goes in with respect to, several machining trials, developing a first article, looking at different processing parameters, and then that is then fed into the initial production, where you now have to understand how you're going to post-process the part that you've printed, and the regulatory requirements that come along with it. And then you essentially test your powder, test your part, and once you have met all the qualifications, you essentially get into scaling up and incorporating quality control in supply chain before you commercialize. So essentially, if you look at the entire AM program, customers can face multiple years and several $1 million depending on the scope of the initiative. And this is where Carpenter additive comes in, and some of the key differentiating factors that essentially are our value proposition when you compare some of our competitors, like a typical service bureau, a typical materials provider, or just an AM equipment manufacturer. Right? I mean, Carpenter, being a metallurgical powerhouse, we have access to the knowledge that is required to develop custom alloys for specific applications. We are able to produce the powders, characterize the powders, develop additive manufacturing print sets, and then further, with using our engineering support, we are able to take that to a dynamic scale-up approach with full post-processing capabilities and prototyping and full-scale part production all under one roof, which helps to accelerate product development timelines. So just a quick overview of our end-to-end solutions facilities. Several strategic investments across different areas. Our AM Tech Center in Reading deals with a lot of TRL 0 to 3 developmental work, which is essentially early stage research. Here we have a few laser powder bed fusion equipments, a DED, and some bind jet equipment. It essentially develops and commercializes new materials. Our Emerging Tech Center in Athens, Alabama is equipped to take the material solutions developed at the Tech Center all the way to TRL 10 with several laser powder bed fusion platforms, DED, and binder jet across different materials. And our facility in Camarillo also is able to take it all the way to TRL 10, which essentially is full-scale production for all of these materials. Partnering with Carpenter Additive is a good approach because we have the near-term capabilities with respect to developing powders and AM process life cycle steps for our customers, along with a long-term vision to become an AM partner where if the applications translate, you're able to leverage the facilities in-house all the way to full-scale production without looking for an external vendor. And then Carpenter, all of our facilities that you see there are located in multiple locations, so it reduces the risk sole source. It's a digitally integrated supply chain, more than 130 years of experience with materials, so it's a publicly owned and United States-based organization.